Welcome back, eh? Okay, let's finish up. Section 4.1 and our motivation and definition of some determinants. We left off last episode having computed cross products of vectors in terms of components by a certain little almost algorithmic trick. So we're going to define the determinant of a 3 by 3 matrix in terms of determinants of 2 by 2 matrices, and that'll link together with the way we computed cross products before. And this foreshadows what's going to happen in the future when we take determinants of larger matrices. But for a 3 by 3 matrix, A, say the entries are as given, subscripted A's for the first column, subscripted B's for the first row, second row subscripted B's, third row subscripted C's. Define the determinant as, it's a definition, you can't argue with it, as follows. We're defining it as entry A11 times the determinant of what we would get by eliminating the row and column containing that entry A11. That'd leave us with B2, B3, C2, C3. Sounds familiar, because this was what we took for components of cross products of vectors. Then we're subtracting A sub 2 times the determinant of what we would get by eliminating the row and column containing the entry A sub 2. We'd be left with subscripted B's and C's without subscripts 2. Subscripts 2 were eliminated. And then we'll take A sub 3 back to positive for some reason times the determinant of the little 2 by 2 matrix we get by eliminating the row and column containing A sub 3. I mentioned this elimination of rows and columns. This is how we'll address it when we do larger matrices. And this is very similar. This coefficient-wise was what we had for the components for the cross product of 2 vectors in R3. So in fact, we could compute the cross product of vectors by symbolically taking the determinant of this 3 by 3 matrix. I say symbolically because matrices have numbers as entries, not vectors. But the manipulations are identical to what we would do up here, and that allows us to take cross products using determinants of 3 by 3s. One more time. The determinant of a 3 by 3 matrix involves 3 determinants of 2 by 2 matrices. When we define it, the determinant of a 4 by 4 matrix will involve 4 determinants of 3 by 3 matrices, each of which involves 3 determinants of 2 by 2 matrices. So this thing's growing like crazy. So to do a 4 by 4 determinant, we'd have to do 4 of these. That'd be 12 determinants of 2 by 2 matrices, and so forth. If we did the determinant of a 5 by 5, I think that'd be 60 determinants of 2 by 2s. So either we're going to do a lot of these big matrices with big numbers like 5 by 5, or there must be a technique to somehow simplify that. Oh, your favorite number, 0. If we had a bunch of zeros in here, well, we might still have to do some of the arithmetic, but it'd be way simplified. So introducing zeros, and we've done that with row reduction, introducing zeros would simplify taking determinants. But for now, 2 by 2 and 3 by 3, that's our problem. Theorem 4.1.a says, and the supplemental Beamer notes have an argument of this. It's not terribly enlightening. Let's skip the argument in the video. It's a bunch of algebra. It says the area of the parallelogram determined by B and C in R3 is the magnitude of B cross C. We had area of a parallelogram determined by 2 vectors previously, and that was 2 vectors in R2. And it didn't involve cross products. So this is rather different because it deals with vectors in R3, and it deals with cross products. Before, we didn't have any of that stuff. In fact, we used the stuff before for vectors with 2 components to motivate the determinant of the 2 by 2 matrix. Anyhow, let's use this, which is a little more tangible to what we did in 2 dimensions. We talked about areas of parallelograms there. Here we're talking about volumes of boxes. Boxes determined by vectors A, B, and C in R3. Previously we had 2 vectors in R2. Now we got 3 vectors in R3. And the claim is the volume of the box determined by 3 vectors is given by volume equals the absolute value of this thing here. This thing here is vector A dotted with vector B cross C. Notice the cross product has to be done first. It only makes sense to take a dot product between 2 vectors. A is a vector, B cross C is a vector. It only makes sense to take cross products between 2 vectors. If we did the dot product first, that'd give us a scalar. And a scalar cross a vector, that doesn't make sense. If you like, we could put parentheses around the B cross C. It's unnecessary because it would be meaningless if we tried to do it in any other order. Wouldn't hurt to put it there for sure. But it is unambiguous what's done first by the way that you compute dot products and the way you compute cross products. Let's actually look at a proof of this one because it's got pictures and it's a little more tangible. Okay. So, get me out of the way. The volume of the box determined by vectors A, B, and C is as given. First off, there's what they mean by the box determined by A, B, and C. So they've drawn it here in such a way. This is a little special, but it gives you a perspective you can see. Vectors B and C are kind of down here in the floor in the XY plane maybe. And vector A comes up off of the floor at an angle with respect to the vertical. Now the reason they've introduced the vertical here is they're taking vector B cross vector C and take them fingers of your right hand, wrap them in such a way that they go from vector B to vector C, from vector B to vector C, and sure enough, your thumb will be pointing upwards. So they've introduced B cross C in this sense in the angle theta, which is the angle between B cross C and vector A. And the box they're talking about is this shaded thing here. I've mentioned before, sometimes this is called a parallelepiped. Okay, volume of the box is the height times the area of the base. You know how to find the area of the base? Yeah, that's a parallelogram determined by vectors B and C. And we had a way to do that. Actually, it was theorem 4.1.a that told us how to find that area. So we'll dredge that up. All right, the area of the base was, by theorem 4.1.a, it was the norm of B cross C. Okay, we just need to figure out the height then. So I'm going to need to bounce back and forth. This height, let's call it H. How are you going to determine that? Well, here's a little right triangle. It has the desired height as the side adjacent to angle theta, and it has hypotenuse, the magnitude of vector A. So adjacent hypotenuse reminds me of cosine. Cosine of theta would be H over the magnitude of A, or H is the magnitude of A times the cosine of theta. H is the magnitude of A times the cosine of theta. So there's your height. How about we write that as the magnitude of B cross C divided by the magnitude of B cross C times the magnitude of A times cosine of theta. Oh, excuse me, I need an absolute value in there. Height would be non-negative. The cosine could potentially be negative here. So we've actually just multiplied by this over itself because we need it to simplify some things. Now we've got in the numerator a product of the magnitudes of 2 vectors times the cosine of the angle between them, absolute value of. That's what the dot product was. The dot product of 2 vectors was the product of the magnitudes times the cosine of the angle between them. If we go back, so we're talking vector A and vector B cross C, go back, whoops. Then, yeah, here's vector B cross C, here's vector A, theta is the angle between them. So we can relate the cosine of theta to the dot product of those two vectors. We can relate the cosine of theta to the dot product of those vectors and their magnitudes. So this numerator is the magnitude of one vector times the magnitude of the other times the cosine of the angle between them, absolute value of, so I'm still stuck with the absolute value over here. That would be the first vector, B cross C, dot the second vector, vector A, absolute value of. So we're still stuck with some weirdness in the bottom, but anyhow, here's the height expressed in terms of some dot products. You like that? Remember where we're trying to go. We're trying to relate this to this numerator. Okay, so if we want to know the volume of the box, it'd be the area of the base. We decided the area of the base was the norm of B cross C by the theorem we previously had. And the height, well, here's the height. So we'll take the norm of B cross C times this height H. Now you see why we wanted to do what we did. It allowed us to introduce the dot product. We get cancellation here, and we get the absolute value of B cross C dot A. And that's what was claimed, right? Well, they've reversed the order on the dot product here. We do have commutativity on dot products. We don't have, actually, I guess we don't have anything on cross products just yet. Properties of cross products are coming up. Well, you don't have commutativity with cross products, but we do with dot products. So I can reverse the order here and draw this conclusion. And the parentheses are included here if you like. So there's volume of a box expressed in terms of absolute values of dot products and cross products. You see any determinants in here? This looks a lot like determinants. In fact, this is the formula we had for determinants of a 3x3 matrix. So back to the notes. Oh, the volume of the box determined by A, B, and C. Well, we can take those vectors, put them in a matrix. First vector, first row, going in as rows, a little weird. Second vector, second row, third vector, third row. Take a determinant, then we'll need an absolute value. Volumes, of course, are non-negative. Determinants can be positive or negative. And it doesn't fit very well, but the determinant would be A1 times the determinant of the little minor matrix, we'll call it, B2C3 minus B3C2. Well, there's your A1, B2C3 minus B3C2 minus A sub 2 plus A sub 3, and so forth. This is exactly this. So there's a way straight from determinants to calculate the volume of a box determined by three vectors in R3. So we've related areas of parallelograms of two vectors in R2. Two vectors in R2 determine a parallelogram. We related its area to the absolute value of a determinant. Raise everything a dimension. Three vectors in R3 determine a box, parallelepiped, a box in R3, and you can find its volume by taking the absolute value of a determinant. So there certainly appears to be a developing pattern. Let's illustrate that with a couple of examples to the supplements. Okay, next. Find the volume of the box having the vertices, having the vectors in standard position as given as adjacent edges. So as in the picture we had in the previous proof, we've got three vectors. They determine a box, find its volume. Okay, well, take those vectors, find their components. So translate from this IJK notation into the square bracket notation. That gives us the three vectors we just saw. Put those in a matrix. as rows. It's the first time we've done this stuff with rows, and it's about the last time we'll do this stuff with rows. I think it's isolated to this section. Otherwise, vectors have gone into matrices as columns. You know the story. So we'll put these into matrix A as rows. All right. So vector A, first row, vector B, second row, vector C, third row. All we got to do is take the absolute value of the determinant, and that's the volume. We seem to have kind of buried the cross product stuff that seemed to be necessary by the previous result. So absolute value, outer bars, of the determinant, inner bars mean take the determinant, outer bars mean take the absolute value of that, is the absolute value of 2 times the determinant of this little 2 by 2 matrix. Eliminate the row and column containing entry 2, leaves you with -1, 2, 3, -8. There you go. Minus 1, eliminate the row and column containing the 1, leaves you with 3, 2, 1, -8, 3, 2, 1, -8. Plus this entry, eliminate the row and column containing it, leaves you with 3, -1, 1, 3. There you go. And crunch the numbers. So taking the determinants of the 2 by 2s, doing the arithmetic, that reduces down to, is it positive? We've got 4 plus 26, that'd be 30, minus 40. We actually get -10 for the determinant, but we're taking an absolute value of it, and we get a volume of 10 cubic units, whatever the units are. So there's a quick way to find volumes of boxes using vectors and determinants. We're motivating the computation of determinants with these little geometric ideas of areas and volumes. Here's one that's virtually the same type of manipulation. It says, use a determinant to ascertain whether these 4 points lie in a plane in R3. Okay, so they've given us 4 points, not vectors, and they've asked us a question about them being coplanar, it's called. Okay, let's do this. Let's introduce vectors. Notice one of the points they gave us is the origin. So let's take vectors from the origin to first point, origin to second point, origin to third point. That way those 4 points will give us 3 vectors. The vectors which are readily interpreted as being in standard position. They could be anywhere. But take the vectors from 0, 0, 0 to each of those 3 points. That will produce vectors. Of course, that produces the vector with components 2, 1, 1 instead of the point with coordinates 2, 1, 1, taking total advantage of the fact that we're doing something here in terms of standard position. You don't like that? Fine. You take a vector from the last point to the third one, from the last point to the second one, and from the last point to the first one. Totally different looking bunch of vectors. You'll still be addressing a similar question. Which is going to boil down to volume of a box. So we'll introduce those 3 vectors. Okay, now those 3 vectors determine a box in 3 dimensions. If those 4 points are coplanar, then these 3 points here are going to all lie in the same plane, and they ain't going to determine a box. Or they're going to determine a box with height 0, say. So we're tying this in with the volume of the box stuff by converting the points into vectors and addressing what's the volume of the box determined by those 3 vectors. We get out 0, we're getting out 0 because those points lie in the same plane and because these 3 vectors must lie in the same plane in standard position. We don't get 0 out, then we're getting a legitimate box with a base, width, and height. Okay. So we've got the 3 vectors A, B, and C. We'll put them in a matrix as rows. Okay, matrix A, vector A, vector B, vector C. We'll find the volume of the box, and we're seeing if that's 0 or not to answer the question they ask about coplanar. Okay, so we'll take the absolute value of the determinant of that matrix A, absolute value of the determinant, here's matrix A, do the homework. You'll get plenty of practice at this and get familiar with a little pattern. But we've got 2 times the determinant of the little minor matrix and so forth. Do the arithmetic. Looks like we get 22 out with the absolute value processed if necessary. What have we got here? Negative 16 minus 10 would be negative 26 plus 4. Yeah, it'd be negative 22 with the absolute value produces 22. Anyhow, it ain't 0. So the volume's not 0. Those planes do not lie in the same plane in R3, or we would have had a box with volume 0. Back to the notes. And properties of cross products. Okay. Cross products peculiar to R3 satisfy the following. Some surprising, some not so surprising. It's anti-commutative. B cross C equals negative C cross B. So if you reverse the order on the cross product, that introduces a negative sign. You got a geometric reason for that making sense? Well, if I curl the fingers of my right hand from A to B, I might get this kind of thing. I reverse the order and I want to compute C cross B, well, I have to turn my hand over and it reverses the direction of the cross product. So there's a geometric argument. We'll give an algebraic argument because that's my job. But there's a geometric argument that we get anti-commutativity. So if you believe that right-hand rule stuff, then anti-commutativity is not a surprise. It's better than just reversing the order and who knows what happens. That was the case with matrices. You reverse the order on a matrix product might not even exist depending on the size of the matrices. At least the cross product still exists when I reverse the order, but it's not the same thing we started with. But it's closely related to it. It's related by a negative sign, opposite direction. We don't have associativity. It isn't true that A cross B cross C equals A cross B cross C in general. That's not true. So we don't even have associativity with this cross product operation. We do have distribution, A cross B plus C, A cross B plus A cross C. So we've got distribution of the cross product over vector addition. On the left and the right is the claim here. Since there's different behaviors on the left and the right, apparently I reverse orders and different things happen. The perpendicular property, B dot B cross C and C dot B cross C, both of these are 0. 0 is right, 0 scalar. Yeah, it's a dot product. So yeah, 0 scalar. Oh, dot products are 0 when vectors are perpendicular. So we can express perpendicular in terms of dot products being 0. This is the linear algebraic way of saying vector B is perpendicular to B cross C, and vector C is also perpendicular to B cross C. So B cross C is perpendicular to both B and C, as stated earlier, and it's to be shown here. The magnitude of a cross product is the area of a parallelogram determined by these. We mentioned that earlier. It's to be shown now. Volume of a box was determined by A dot B cross C. Well, I need absolute values in there. They've stated it as plus or minus volume of the box. And there's a little claim here that that can also be written as A cross B dot C. There's a little trick with what's going on here. The vectors, let me just leave it at that. There's something to be established that these are equal, because that's not at all clear that these two are equal. The fact that they equal the volume of a box, I don't know, I guess it was determined for this quantity here upstairs, and was that the second theorem that we did? And then this funky little relationship here about taking a cross product of 3 vectors. We don't have associativity, so I need to give you some parentheses in there. Claim is A cross B cross C is given by a difference of B and C, where the coefficients of those respective vectors are determined by dot products. I'm thinking we're not going to make a whole lot of use of number 7, probably minimal use of number 6 as well. Probably the most important in terms of your future experience is this perpendicular property. The cross product, excuse me, the cross product is perpendicular to both of the input vectors, B and C. In terms of math properties, this anti-commutativity, that's pretty wild. There's other algebraic structures that have these kind of conditions. One of them you might encounter in an upper level algebra class called the Quaternions. And I just happen to have my Quaternion shirt on today. It's a structure where multiplication of the elements of that structure is rather similar to this anti-commutativity cross product stuff. Let's run through proofs of, that's a video, we got all the time in the world. Let's run through proof of a couple of those. And then we'll do a final example. The proofs of the rest of them are exercises. Let's go through a proof of anti-commutativity because that one's a little surprising, maybe algebraically, geometrically with the hands, maybe not so much. And let's go through a proof of one of the distribution properties. Okay, back to the supplements. Next, let's prove anti-commutativity. This is an example in the book, I guess. Okay, so let's take B cross C and show it equals negative C cross B. This is going to be algebraically kind of ugly, so it's not pretty. It's not terribly enlightening. And the result, if you'll think geometrically, the result's not terribly surprising. But I owe you an algebraic proof, so here you go. Okay, we'll take that cross product. There's a good chance to practice taking cross products, eh? Defined like this. We've taken the components of B as a second row, the components of C as a third row. We put the IJKs in the first row. We've produced this thing here. Or if you like, straight from the definition of cross product, we get this thing here. Now I got to do a bunch of little determinants of these 2 by 2 matrices. So I'll compute those. It gets a little messy. Tell you what, let's factor a negative out of this. Okay, so if I factor a negative out of the first piece here, that'll require us maybe to reverse the orders on these. So we'll have B3C2 minus B2C3. Take the negative, distribute it back in. Sure enough, it produces that. Let's take a negative out of this expression. I need to take a negative out of all of this. I want to leave that negative up front and have this expression pay for the factoring of the negative, where we just reverse the orders again in that difference. Same thing over here, reverse the order in the difference. So we factored a negative out. Why would we want to do that? Well, remember what we're trying to show. I'm trying to get negative something or other. Well, if it's true, what's left ought to be the something or other. And look at this, you got B3C2 minus B2C3. Well, that sounds similar to what we've dealt with before. If I go back up to the straight product, the straight cross product B cross C, we had the positive as the B sub 2, C sub 3, and here we've got it as a negative. Well, we can resolve that by putting the C's in the top row and the B's in the bottom row in the second row. And then when we take a determinant here, we'll get C2 times B3 minus C3 times B2. C2 times B3 minus C3 times B2. And similar things happen over here. So by introducing the negative, we can rewrite these in terms of having the C's in the top row, components of C in the top row, and components of B's in the bottom row. And dude, hey, that stuff in parentheses, well, it's the cross product. It's the cross product of C with B. It's C cross B, because the C's come first and the B's come second. Now, there's something awfully suggestive in this, that when we swap these rows, effectively swap the rows in each of those little minor matrices, seems to have resulted in a negative sign coming out. Not a coincidence. We'll see this as a general property of determinants down the road when we define determinants in general. But there you go. There's your anti-commutativity, and there's algebraically why it's true. How about distribution? Let's establish that. So claim is A cross B plus C equals A cross B plus A cross C. Okay, let's write them in components. So let's take A, B, and C, write them out as components. Let's do the vector addition first, add vectors component-wise. So we get the vector A1, A2, A3, cross product, the vector B1 plus C1, B2 plus C2, B3 plus C3. Cross products, taking those as, symbolically, determinants of 3 by 3 matrices with the i's, j's, k's, components of the first vector, second row, that'd be the A1, A2, A3, components of the second vector in the third row, B1 plus C1, B2 plus C2, B3 plus C3. That is, by definition, the cross product of those two vectors. All right, so we're trying to expand this out. And remember, we're going to try to arrive at the right-hand side of this equation. So we're turning the left-hand side into the right-hand side. Okay, off we go. All right, so we'll expand that out in terms of determinants of 2 by 2s. And this ain't going to be pretty. So we'll have A2 times B3 plus C3 minus A3 times B2 plus C2, and so forth. So that's what's going to happen next. I told you, A2 times B3 plus C3 minus A3 times B2 plus C2, and so forth. So here's the components of the others. All right, trying to collect these together into something recognizable. Let's see, how about we distribute? Okay, so let's distribute the A2s in that first term, the A3s in that second term, and so forth. So there's a bunch of distribution to be done. You can't argue with the validity of that. And that produces this. Let's regroup things. Right, it's kind of a reverse engineering style proof. And why you would do this? Well, you'll see why when we see that it leads to the answer. Okay, let's group together the A2B3 and the A3B2 with the negative. Let's group these two together, and let's group these two together. Let's group the A13 with the B31, the A1C3 with the A3C1. Just moving some things around. There's numbers, commutativity, associativity. Okay. And these little things are themselves determinants of some things. So it's got the pattern. We've got no subscripts of 1, no subscripts of 1, no subscripts of 2, no subscripts of 2, no subscripts of 3, no subscripts of 3. And we can actually write those as a bunch of determinants of 2 by 2 matrices. Why would you want to do that? Because we're trying to get this in terms of a cross product. And cross products have coefficients that are determinants of 2 by 2s. So we can rewrite these as the corresponding determinants of 2 by 2s. We've got an I, a J, and a K. Where were we going with this? We wanted a sum of 2 cross products, if you look back at the original statement. So let's peel these apart, maybe with the A's and the B's together and the A's and the C's together. All right, so let's see there, we've gotten rid of the parentheses, and here we've got the A's and the B's together and the A's and the C's together. So it's just some algebraic manipulations. We're good, we're dealing with vectors and numbers at this stage. So we got all the commutativity and associativity stuff we need there. Oh, hey, wait, why, that's just A cross B. You got the I, you got the negative in front of the coefficient to the J. Same thing down here, except we got A's and C's. This term is A cross B. This term is A cross C, and that's what we were trying to show. That A cross B plus C equals this quantity here. We started with the left-hand side, fiddled with it, and turned it into the right-hand side. Those are algebraically equivalent. So there's a couple of properties of cross products established. Like I said, the rest is homework. Let's take advantage of the properties of cross products and do one last example. Call it a day on this section. Take three vectors A, B, and C in R3. Simplify the expression A cross B cross C plus B cross C cross A plus C cross A cross B. Okay. One of the properties, so one I said we're probably not going to use very much, was a relationship between a cross product of three things and some dot products. It was exactly this: A cross the product B cross C equals dot product times B minus dot product times C. So what we can do is expand all three of these according to this rule. Be careful. So I'm interchanging the roles of A, B, and C to be played by the characters B, C, and A respectively in this one, and then C, A, and B respectively in the third vector. So that produces these two additional equations here. So we want to add together the three given things. Okay, we can substitute and write them as these linear combinations involving dot products. Okay, we've got, geez, quite a mess here. Let's collect together multiples of B. We've got A dot C times B, no B's, no B vectors, B's and dot products, but no B vectors. Here's one, and a negative C dot A for B. So we got A dot C minus C dot A. Oh, dot products are commutative. So that'll be a coefficient of 0. With the C's, we've got a negative A dot B and a positive B dot A. Excellent, same story. We'll get a coefficient of 0 there. That just leaves the A's, and we've got a negative B dot C and a positive C dot B. Commutativity, we'll get zeros for all those coefficients. We'll get 0B plus 0C plus 0A. Oh, and that'll just leave us with 0. No, the 0 vector, because it is still a linear combination of vectors. So this quantity with that little property 7 for properties of cross products simplifies down to just the 0 vector. So there you go with cross products and some properties of cross products and motivation of determinants in terms of finding areas and volumes. So far, what we've done is only determinants of 2 by 2 and 3 by 3 matrices. We're going to do determinants of n by n matrices ultimately, and it's going to be a recursive process. That means it's going to be computationally nightmarish unless there's a shortcut. And we'll know some shortcuts. And 0 will be your friend to simplify things. Have a nice day. There we go. Let me call this thing to an end. Stop sharing. There we go. Bye-bye.